All right, Hassler's back, part 2, 2.5, evaluating limits analytically. Today we're going to do more with the manipulation, and it's slightly more difficult manipulation than what we were doing by just factoring. So when you're evaluating limits by substituting numbers in, if you end up getting that indeterminate answer, 0 divided by 0, you have some manipulation of the function to do. Yesterday we saw that one way to manipulate is to factor. Okay, another way to manipulate is to multiply by the conjugate or deal with trig identities. So we're going to deal with the trig stuff in this video. And so I'm just going to start with problem 5. If you just want to pick up where you left off in your notes yesterday, we're going to start with problem 5. So the limit as x approaches pi halves, and then I'm going to have tangent of x divided by secant x. Okay, and so I'm going to go ahead and substitute pi halves in, tangent of pi halves over secant of pi halves. And I know you're thinking, Hassler, what are you doing to me already? Yeah, I know. If we look at the unit circle, right, pi halves is at the top of that unit circle. And the ordered pair for pi halves is 0, 1. So this is why I had you looking at your trig stuff yesterday. Okay? All right, tangent of any angle measure is the y-coordinate divided by the x-coordinate. Well, in this case, if I do 1 divided by 0, I'm going to have undefined. That doesn't bode well, does it? And secant of any angle measure is the reciprocal of cosine. Okay, so if cosine is the x-coordinate, then the reciprocal of that would be 1 over the x-coordinate. And again, 1 divided by 0 is undefined. Now, if you look at these things graphically, I believe the graph for a tangent function looks something like this. And you have a vertical asymptote at pi halves. So on the left side, you're headed towards positive infinity. On the right side, you're headed towards negative infinity. And so this is why we're getting, essentially that it looks like the limit does not exist. I'm undefined, or I'm headed to infinity on one side, negative infinity on the other. Secant is going to be a similar graph. Secant also has vertical asymptote at pi halves, and secant looks something like this, alternating parabolas almost, even though they're not parabolas. Okay. All this to be said is that I'm going to be indeterminate. This is indeterminate. I cannot determine what the limit is at this point. So what I have to do is some manipulation. I'm going to rewrite the limit as x approaches pi halves. And I somehow have to manipulate the tangent, or manipulate the secant, or manipulate both of them. And this is why you need to be familiar with or comfortable with the trig identities. And so the first trig identity we're going to use is a quotient identity. The quotient identity, one of them states that tangent of x is equal to sine of x divided by cosine of x. And this quotient identity is very popularly used by AP. It's a very common one to use, and so I would square that away in your brain, like, hey, I really need to know how to rewrite tangent in terms of sine and cosine. And the other identity we're going to use is a reciprocal identity. Again, I had said over here off to the right that secant of theta was the reciprocal of cosine. And so secant of x could be rewritten as 1 over cosine x. And again, they like to use the reciprocal identities. Cosecant is 1 over sine of x. Cotangent is 1 over tangent of x. Okay? And my strategy when it comes to these trig functions, my strategy is to rewrite using sines and cosines if possible. hey, it might not always be possible, okay? There are always exceptions to the rule, and in math I feel like there are more exceptions than not, okay? But my strategy here is to turn tangent and secant into sines and cosines. All right, the reason why I do that is because I can now rewrite this limit is equal to, I'm not going to substitute pi halves in yet, I still have some manipulating to do, so I have to rewrite that limit as x approaches pi halves. And when I have a term, in this case sine x divided by cosine x, divided by another term, 1 over cosine, dividing by 1 over cosine is the same as multiplying, so I'm going to take this sine x over cosine x, and I'm going to multiply by the reciprocal of 1 over cosine. So dividing by a term is the same as multiplying by the reciprocal of that term. Okay? Dividing by a term is the same as multiplying by the reciprocal of that term. Look it up if you need to, okay? Hey, look what happens. I have sine times cosine, really technically in that numerator, and in the denominator I have cosine times 1. Well, hey, because these are being multiplied in the top and cosine times 1 in the bottom, I can divide a common factor out. Look, I'm still not applying the limit yet. I'm not substituting in, so I'm going to rewrite the limit as x approaches pi halves, and all I have left is sine divided by 1, which is just sine of x. So I've taken my complicated expression, tangent divided by secant, and I've simplified this to sine of x. And now I can substitute pi halves into my function, which means I'm going to finally drop that limit. And sine of pi halves, well, sine is the y-coordinate of the ordered pair on the unit circle. Okay, so at pi halves, the y-coordinate is 1. Sine of pi halves is 1. Okay, which is why I had the unit circle out for you guys, so that you could take a look at that unit circle and start to, store that away in your brain as well. Okay, let's do another one. I have the limit as x approaches 0. We have sine x divided by tangent x. Okay, again, if I evaluate, I've got sine of 0 divided by tangent of 0. All right, so again, let's look at this unit circle. When I talk about 0, I'm talking about 0 radians or 0 degrees. The ordered pair is 1, 0, my fault. The ordered pair there is 1, 0 at 0 radians or 0 degrees. We use radians in math, okay? And sine is the y-coordinate, so sine of 0, the y-coordinate at 0 is 0. And tangent, we said, is the y divided by x, and 0 divided by 1 is 0. So look, I'm indeterminate again, which means I need to do some sort of manipulation. So I'm going to start back at the beginning, rewrite my limit, the limit as x approaches 0. And I said on the last problem that my strategy was to rewrite in terms of sine and cosine, if possible. Well, I already have sine x. But I could rewrite tangent. And I hope you recall that we rewrote tangent as sine of x divided by cosine of x. And the reason why I put this division bar in red is just so I can line it up with the original division bar, okay? So this big division bar under the first sine of x is the original division bar in my original problem. Again, when I'm dividing terms, taking sine of x and dividing it by sine divided by cosine feels complicated. So this is equivalent to the limit I have not applied the limit yet, the limit as x approaches 0 of sine of x times the reciprocal of that denominator. If you need to go look that rule up, go look it up online, okay? That dividing by a term is equivalent to multiplying by the reciprocal of that term. Hey, this is really nice because, sine of x is the same as saying sine of x over 1. Look, I have sine times cosine in the numerator. I have sine in the denominator, and those two things are going to divide out. I'm really applying the limit as x approaches 0 of just the cosine function. And again, I erased it, but the cosine function is the x-coordinate on the unit circle, and at an angle measure of 0 radians, the x-coordinate is 1. All right, I'm going to do one more trig problem. I have the limit as x approaches pi halves of 1 minus sine x divided by cosine squared x. And again, if I evaluate, 1 minus, sine of pi halves is 1. All right, this is like saying cosine of pi halves and then squaring that answer. Okay, we'll talk more about that as we move throughout the year. Cosine of pi halves is 0, and 0 squared is 0. And so again, I'm indeterminate. So my job is to rewrite and manipulate. Well, I already have sines and cosines, and so you're thinking, Hassler, what's your strategy here? Yeah, I have a strategy. The other big deal on your trig identity paper are called Pythagorean identities. And Pythagorean identities show that if you have sine squared x plus cosine squared x, it equals 1. Okay, well, in my problem back there, I had cosine squared in the denominator. So if I subtract sine squared x on both sides, I'm left with cosine squared x equals 1 minus sine squared x. That's my manipulation, and I'm going to replace cosine squared with 1 minus sine squared. If you need to pause the video and go back and rewatch that part, rewatch it. My idea here, though, is to use that Pythagorean identity so that I now at least have the same trig functions. Why would you do that, Hassler? Well, because I have lots of experience and I can see what the answer should be. All right. Because the denominator is a difference of perfect squares. This right here is a difference of perfect squares, which we saw yesterday with, normal terms, x squared and 25. But I can factor this into 1 minus sine x and 1 plus sine x. If you're unsure of that, you could multiply through to double check, right? You could distribute each term in the first group with each term in the second group to check it, and it would work out that you get 1 minus sine squared. And the reason why I want to do this, I hope you can see, is because this entire numerator, 1 minus sine x, is going to divide with one of the factors in the denominator. So what I'm left with is the limit as x approaches pi halves of 1, everything divided out. So I have nothing left in the numerator. Well, remember, 1 minus sine divided by itself is 1, okay? Divided by 1 plus sine x. And now I can go ahead and substitute in. I have 1 over 1 plus, sine of pi halves is 1. So this whole thing is going to simplify to 1/2. So you've got some trig to work on. I'm going to go ahead and do a second video on another way to manipulate. Talk to you in a few.